I think this is a homemade sub that someone's messing around with in some lake somewhere in North America, I suppose, but I don't know exactly. So it's kind of curious. And it's germane to what we'll talk about today, because what we'll talk about today is we'll move from pressures on structures to talking about buoyancy. And so buoyancy relates to fluid pressures, of course, in the same way. This is, I guess, I'm not sure it's an emergency breaching, but it's a breaching of a sub, a nuclear sub, onto the surface. It involves, of course, the ability to be able to submerge by changing around with your buoyant weight, and also by rising to the surface. Not without problems. There's the USS Greenville was a sub somewhere in the Pacific off Hawaii that chose to do one of these emergency breachings and happened to do it, unfortunately, underneath a ship. The ship happened to be a trawler, which is basically a training boat for Japanese fishermen, your age probably, training to be fishermen on the high seas, and the boat sunk as a tragic outcome. And so another example of buoyancy. The other one, when was this? This was, when did it sink? So the refloating activities were 2013. This was the Costa Concordia. This is a cruise boat sailing around in the Mediterranean. The captain decided to show off by doing a pass by an island, got too shallow, scraped a hole in the bottom, and luckily for them, although it sank basically on a ledge, and this is where it came to rest. And the salvage operation to get rid of it, I think 40 people died, was to refloat it. And so to refloat it, they built an arrangement to physically pull it down onto this rig, have tanks which originally were weighted to be able to pull it over with a moment, and then ultimately those tanks were evacuated to be able to float it up and then remove it off to, I think, to salvage. I'm pretty sure to salvage. And so what we'll talk about today is buoyancy, after we finish off our final discussions on forces on structures. So that's our plan for today. So let's see where we are. We are at the end of week 3, so we're 3-3. If I can find where we are. And as usual, we have a preview of exactly what we will talk about. So, our discussion today will end up on buoyancy, but of course buoyancy is really part of fluid statics and pressures. We've made the point, it's probably worthwhile restating this, just because it's such a key part of what we're dealing with. And that is that if we have a liquid, and we have, say, a structure underneath that liquid, which is of some length, and I won't draw it in the third dimension, but this is the water surface. We can always calculate the magnitude of the force acting on that if we know the unit weight of the fluid, if we know the area of the plate, and if we know the depth to the centroid, H sub c. Very specifically, it is the depth to the centroid. It is not the in-plane length, but it's the depth to the centroid. That is how we calculate the magnitude of the force that would act on this, which would be F sub r. If we want to know where that force acts, it does not act at the centroid. It will act at the centroid if the fluid pressure is uniform, but that's rarely the case. And so to calculate exactly where it acts, we have a variety of things that we can do. The first one, so we know exactly where it acts. What we'd like to know is where it acts, and to do that, we will make a coordinate system which will be directed along this plate in the y direction. It will have its origin at the surface, where it intersects the surface. And we'd like to to know the magnitude, the location where it acts. So although I've drawn this here, let me take that out. The magnitude of the force is this, but it doesn't act at that point. It will act at a separate location, which will typically be below the centroid of that plate. And we want to calculate this distance y sub r, the location of the resultant. And that location of the resultant is offset from the y-coordinate of the centroid, y sub c, by some small amount, by this amount here. And so we can figure out exactly where that location acts in three ways. The first way is to realize that the fluid pressure distribution on that plate will look like, will look like a linear distribution that doesn't start at 0 at the top. And what we can do is we can make that into two parts. One which is a triangle, where we know that the force of the triangle acts at 2/3 of the length down its length, if this total length is 1. We have a force for the square, which acts at half of its length down the length. And we want to figure out exactly where the resultant acts, which is some distance L sub r, I guess, from the same location. And so we know that we can calculate the forces from the areas underneath these pressure diagrams. So we know we can get F delta and F square. We know exactly where they act. We know that Fr is going to be equal to the sum of those two. And so we can take moments around any point, which will give us the moment that Fr has, multiplied by the length of that lever arm, which is this. And that has to be equal to the force due to the triangle multiplied by 2/3 of the length plus the force of the square multiplied by half of the length, and the total length is 1. We know that this resultant is equal to the sum of the triangle and the square, and so the only parameter we have is this. We can calculate LR. So that's one way you can always do it. You can always do it that way. The second way you can do it is to, if I go back into this mode, is we can take this, I'll draw it in perspective now. This is the plate that we have. We know that if we look at that plate, we can calculate the force in the same way, but we can calculate the location where the resultant acts, which will be this point here, F uppercase R. And if I draw this here, this will be Y sub R, where this is the surface of the water. This is where it intersects the surface of the water. This is the centroid, which is Y sub C. And we can always get it by using this expression here. Y sub r is going to be equal to this apparently slightly complicated expression, but this is a standard result. This is b cubed times a over 12, as you saw last time, the geometry of this plate. The slope distance of the centroid, the area of the plate, which is this area here, plus the slope distance to the centroid. So in other words, this always tells us, since this number is always can be 0 or greater than 0, always positive, is always going to be slightly below it, as you'd expect from this from looking at the moments. Same rationale. But this gives you it in one step, and you calculate the resultant in the same way as well, just by using this, where this is the depth of the centroid. So this is this, H sub c. And the third way is the way that one of the ways that we'll talk about today is using free body diagrams. And so very straightforwardly, I guess, what you could do is if you had this plane here that intersects the surface, you could draw a free body diagram that included this, that had a triangular pressure distribution on the side, a triangular pressure distribution on the side. It would be a weight of this fluid acting downwards, and it would also be a triangular distribution on the side. So let's not talk about that now, but let's move towards dealing with that. And you can resolve all the forces. So that's the third way that you might have to use. Everything we've talked about so far has been on flat surfaces, a plane. The submarines that you saw are curved surfaces, and so we have to maybe take a different tack to that. The other expression that we'll use today, which is related, of course, to fluid pressures on structures, is the buoyant force that acts on components. And let's just deal with that before we move on. You've probably seen this before. It's Archimedes' principle. So let's talk about buoyancy. And the idea is just this. We know that fluid pressures, as you go down within a fluid, will increase linearly according to the unit weight. We know that if we have a bucket, which was our first entree to this, you can think of it as a differential cube as well. We have a fluid pressure acting here, and we have a fluid pressure acting here. We know from this diagram that the two fluid pressures will be different from each other. This is P1 at Z1 and P2 at Z2. P2 is obviously greater than this. This has some height, call it H. And so there's a difference in these pressures because of this. So if you do a equilibrium calculation for F equals ma, it's not accelerating, so this has to be equal to 0. So if we convert these pressures to forces, we know that the force acting upwards is greater than one acting downwards, so it would accelerate. So if F is finite, it would accelerate. So what we have to account for is the fact that there's a weight acting downwards. And we know that when there's a weight acting downwards, this is an equilibrium because that was our equation for fluid statics. Let's make life easy for us and move this bucket up to the surface so that now it sits on the surface. The pressure acting here at pressure 1 is 0 because of the atmospheric. The pressure here is equal to the unit weight times the depth below the surface. And the force that acts at this point, which we'll call uppercase P, is equal to the unit weight times the height, which is the pressure, multiplied by the area. This is the area, which is this top of this figure here. This is the area. The weight acting downwards due to the water is going to be equal to the volume of this bucket multiplied by the unit weight. And of course, the volume is equal to the height times the area multiplied by unit weight. Right? This is this. And so we know that this is in perfect equilibrium because the pressure acting upwards, which is equal to gamma HA due to this, has to be equal to the weight acting upwards, which is equal to gamma HA. This is due to the weight acting downwards, exactly balanced by the pressure pushing up. What happens if you empty out this bucket, a weightless bucket with corners to it, so that the unit weight goes to 0? If the unit weight goes to 0, then this is 0, and there's an extra force that's applied which will pop it out of the water. And so this buoyant force, due to that, is just going to be equal to the unit weight of the fluid times the height times the area, which is equal to what you know already, unit weight of the fluid times the volume. It's the unit weight of the fluid that is displaced, as you know, multiplied by the volume of fluid that's displaced. So this is exactly the same as this expression up here. I'll go down a second. And so that's a standard result. So that's just the easiest way to derive it. We derived it so the top of the bucket is on the surface because there's no pressure on it. We know that it's just a difference between the pressure acting on the top versus the difference. And no matter where you go down here, the difference between those pressures top and bottom for the same height is always going to be the same. And so you can add a pressure on the top, and the difference between the pressures is always going to be an imbalance, which is forcing it upwards. So that's buoyancy as we need it. Okay? All right, so let's go through some examples. I'll switch this back to my favorite red. We'll talk about force on structures, and then we'll move on to buoyancy after we go back there. We'll do these kind of in broad brushes as to how we might approach such problems. So here's the first one. So we made the point that we want to know how to make calculations for fluid pressures on things that aren't flat anymore. One way in which we can do it, if we wanted to try and figure out exactly what the resultant force is that's acting on this side of this pipe, if we cut it down the center line here. So in other words, we cut it on this center line and break it in half. It's actually the third of the methods that we talked about, dividing it into a free body. And so the free body would look like this figure here. And it comprises the actual fluid-filled pipe, which is outlined here. A force that is applied on the side, which of course would be equal to this triangular distribution of pressure growing at depth to some fluid pressure which is equal to 3 times the unit weight at the bottom. If it's not accelerating, it has to be reacted against by a horizontal force which we call F uppercase H. And so those have to be equal to each other. So we know exactly how to calculate this, right? F1 is equal to area, unit weight, depth of centroid. Depth of centroid is going to be what? Area is going to be 3 feet, 1 foot into the page. So this is going to be 3 times 1. And you know the unit weight. So we know what F1 is. Where does it act? It comes in contact with the surface. It's triangular. So the location where it acts is going to be 2/3 of the depth down. So it's going to be equal to 2 feet. The only other forces acting horizontally is FH. It has to be exactly the same location, same elevation, same magnitude as F1. So this has to be the case. Otherwise, the system isn't in equilibrium. So we know now what the force acting horizontally on the outside of the pipe to keep it in place is going to be. Vertical force, well, resolve vertically. The pressure acting on the top is atmospheric, 0. There's a weight of the material. It acts through the center of the centroid of this shape, which is the center of gravity, which is a standard result, which we know from last time, or you should know from statics. And the only force acting upwards is Fv. So we know that this has to be true. What's the magnitude of W? It's going to be equal to the area times the unit weight multiplied by 1 foot into the page, because it's 1 foot length of pipe. So we know what W is, so we know what Fv is. So we know each of those two forces. Where do they act? How do we find that out? Well, in this example in the book, they say, well, the surface is curved, so all the forces have to be acting perpendicular to that surface. And for that reason, all of these forces have to act through the center here, which is true. You don't necessarily know that, but that's the case. What you could also do, if you wanted to know exactly where they act, is that you now know where this force acts, and you also know where this force acts. So presumably you could draw a free body diagram that was like this shape, that had these forces on it. It has force 1 acting at this point. It has W acting at this point. You know exactly where it acts if you look at the location for centroid of a half circle, which is here. 4/3 r over pi, just a standard result. So you know where each of those act. Whoops. And you have another force, Fr. You know what Fr is because you know that W and F1 give you Fr. So you can calculate that if you know each of these. So you know what Fr is. So that you know the magnitude of this, and so you could do the calculation to be able to figure out, take any point that you want, take the moment of F1 times L1, take the moment of W1 times LW, and take the moment of this around some offset for this, and you'll find that it goes through this central portion. So that's the other way to be able to do that. And so you'll find out that actually, because of this geometry, since you know it goes through the center of gravity here, you know exactly where this goes, you'll find out that the horizontal force goes through a point which is given by, has to be somewhere on this line here, on the center of gravity, has to be somewhere on this line here, and it'll be exactly through this point, and its trajectory will be through this point A. And so you can maybe prove that to yourselves. So the working's there. So if you don't quite understand exactly what we're doing, then just go through this at your own pace and figure it out. But it's the third method that we talked about in terms of being able to take moments. Okay. So a slightly, I guess a modification on that, well, actually the same question really, that differs only in terms of what the magnitudes of the forces are, is that to calculate what the force is that's acting at the resultant on this. Again, you can draw a free body. You can isolate this portion, and you can figure out that all the forces that you apply to it have to hold it in one place. And the forces now are slightly more complicated. The same weight is acting down through this as it was before, which is this. The force that's acting on the side F2 has to be a little bit different because now it starts off at this place at some pressure. But of course you can still calculate the F2. What would F2 be? unit weight, depth of the centroid times the area. The depth of the centroid would be halfway down here. So this would be h sub c from the surface. So you can get the magnitude of F2. You can get the magnitude of F1. It would also be the same magnitude. The depth of the centroid is what? This is HC1. This is HC2. So you get this for 2, and F1 would be the same. Unit weight HC1 times area 1. The area, of course, is the length of this section here multiplied by the distance into the page. So you have that. So you have this as well. And to be able to calculate the resultant, F sub r, you can always get the resultant if you know what each of these are. But we don't know what each of these are. So what we need to do is do a force balance. Sum of the forces in x have to equal 0. Sum of the forces in y have to equal 0. And so this is, I'll just zoom out one step. So if you do that in the horizontal direction in x, then F2 has to equal FH. We know what F2 is because we said we can calculate it. And so we can calculate the magnitude of this. We do a balance in the vertical direction. We know F1. F1 plus W has to equal FV. F1 plus W has to equal FV. We know F1 from this expression here. We know the weight that's applied because of the volume, unit weight, volume and unit weight. And so we can calculate what this is. If we know both the horizontal force and the vertical forces, we can calculate the resultant just by using Pythagoras, which is this. And if we wanted to be really smart, we could use exactly the same technique as before by taking moments about a point to be able to figure out where it acts. But let's not do that. So it's just a matter of dividing it up into something that you can imagine cutting a contour around this thing so that you can release it, and then figuring out what forces are applied to it that have to be applied to keep it in place. A fluid pressure on the left-hand side, which is balanced by a reaction by the wall on the right-hand side. A fluid pressure acting on the top, plus its weight, balanced by an upward force of the fluid of the wall at the base. And you can work your way around it. If you know the magnitudes of these, obviously you can also calculate the angle theta from this as well, uniquely. So it's just trigonometry that you have to use. So it becomes a little bit of housekeeping, but I'm sure you guys are up to it. Yes? So, well, look at these and use the TAs if you're having problems with it. Tainter gate. This is a picture of a tainter gate. Actually, I took many years ago now in Nova Scotia. The idea of a tainter gate is that from this idea of these curved surfaces, if the gate is an arc of a circle, then by definition, all the fluid pressures are acting perpendicular to that surface. And so by definition, they are all directed directly through the center of that circle, and therefore there's no net moment applied to this. So if you take the moments of this about this circle, you find that there's zero moment. There's a big force that acts in the horizontal direction, but there's no moment that's applied to the gate. So the net result is that you can make a gate that is pretty flimsy, just with these metal struts in this particular case, and with a flat surface on the back. So a tainter gate is exactly what that is. So we won't talk about that. Mega tsunami, too complicated, too complicated. Let's do some others. So we'll morph into talking about buoyancy in a second, but this may be the final one that we talk about. And let's just talk about this. It's again in terms of how would we solve this problem. So here's a question. You have a cylinder floating in oil. Oil comes up to the top of the cylinder. The cylinder butts against a wall. Not sure exactly what this is supposed to be, why you'd have a big puddle of oil, but no matter. And the question is, what is the force that gets applied against this component here, FA here. And so what do we know about this? How would we deal with this as a free body? Well, if we want to know what FA is, we can just divide it into a free body, and the easiest way is to divide it into one that includes all the different parts of this. So this is the free body that we're going to take. It's kind of outlined here. There's a fluid pressure that acts as we go down here on the right-hand side. Well, I guess the other thing we could also say is that we need to calculate FA, so we need to sum the forces in the horizontal direction, and they need to equal 0. Also, what has to be true is that the forces in the vertical direction have to be 0 also, but we're not asked that, and so we don't care. So we don't care about this. Clearly, if we looked at resolving forces on this body, there's a weight that we have here. There's a weight that we have here of the water. There's a fluid pressure that we have acting on the bottom of our free body, which is this fluid pressure here, which would be FV, but we don't care, because all we need to know is something about the magnitude of the force that's acting. So if we isolate this, what is the magnitude of this force that's acting here? You could rationalize it in a couple of different ways. The important way to rationalize it is you could, for instance, think that this is atmospheric, and therefore the fluid pressure would be this. But that really can't be the case, because we know that if we go from this point here, where the pressure will be this amount, and we go through the fluid to get to this point here, we're still at the same elevation. We know that dp dx equals 0, so, or dp d, let's call it, dp dx equals 0. So the pressure here has to be exactly the same pressure as here. And so really what this has to be a really quite good seal. So the pressure that's acting here really has to be just like it is on the other side. Not the part above this wall, but the pressure distribution is going to be this, which is going to be exactly the same pressure distribution as the blue part that I'm drawing in here. Right? Fluid pressure here has to be the same as this. Fluid pressure here has to be the same as this. And so this blue figure has to look exactly like the blue figure on the other part. And so you can immediately see that the only unbalanced force you have, which is FA, has to be equal to essentially the green part here. And this would be this part here. So that's physically what's going on. So if you do that, you can do the calculation. F1 is equal to what? Unit weight, the area of this plate, which would be this area here. This is the area. The centroid of this plate is going to be equal to this here, which is HC. And we know F1. It's just going to be equal to this distribution here. We know that F2 is going to be given by exactly the same number, or same equation rather. What are those going to be? Well, the plate is going to look like this if I draw it in perspective. The height to the center of this plate is exactly the same as if it was on the other side here. right, from the surface, because that's really where the water is coming from. So in other words, you can think of this as an imaginary surface here, because this is going to be the average magnitude of the pressure, which we'll do here, which is what HC2, this is this here. And the area of the plate is just going to be A2. And so you have this here. And so physically, it'll give you a smaller force acting F2 than F1, and therefore FA has to be a positive number. So this is physically how to do it, but this is conceptually why it looks that same way. The total area of this triangle is acting on this side. The truncated area of this triangle is acting on the other side. And so you have to basically add another green force on the top, which this is equal to FA. Same thing. So you could think about solving it in a couple of different ways. Okay. So the key thing to figure out is that this is not atmospheric pressure acting at this point. And so it has to be sealed. And so you could imagine that since the force acting to the right is larger than the force acting to the left, then it's physically pushed up against this wall, and that's what causes the seal here. Okay? So this is this layout here is basically an exposition of what we just said, and I won't go through this, but I'll let you show this to yourself. This is the idea that we have a gate here, which is inclined, which is of 1 meter high, has water held up behind it. The gate's at 45 degrees, and so we know the length of the gate is 1 meter, so square root 2. It's water behind it. And it's just to make the point that we can solve this problem in 3 different ways, and we should get exactly the same results either way we do it. We could do it by the Centroid Method, which is the first one. Well, it was the second one we talked about when we started off today. And that is, we could look at this as a plate which has a centroid on it. We want to find out where the Y sub R is, and we can do it by figuring out what the force is by this expression, where it acts from this expression, and we find out that these are the forces, and this is where it acts. We could also do it by the kind of pressure prism approach, where we take this gate and we divide it into the pressure prism that acts on it, which we know is this one. So this is really the first one that we talked about today. We know that the pressure at the bottom of the gate is just going to be equal to the depth y times the unit weight. We know that it's a linear distribution. We know that for a linear distribution, the resultant will act 2/3 down the distribution, or 1/3 from the bottom. And so we know where YR is, and we can also calculate the magnitude of the force just by taking half the pressure in this particular case. So in other words, half the maximum pressure would give us adding this amount and subtracting this amount, if you understand physically what we're doing. So we can get the magnitude of the force just by looking at this pressure distribution, calculate it how you want. It's just the area under this triangle, which is equal to half the magnitude multiplied by the total height. Or you could take the magnitude here and divide the total magnitude by half. And the location where it acts is 2/3 of the way along the length of this boundary. And if you really want to torment yourselves, you can also do it by taking a free body. This is the gate. This is the pressure prism that acts on that gate. This is the free body of the fluid underneath it. We know the fluid pressure that acts on the bottom of that block of water. We know the pressure that acts on the side of that water, and we can resolve to figure out exactly what the resultant is. And so certainly we can calculate what this is and know where it acts. Certainly we can calculate what this is and know where it acts. Certainly we can calculate what this is and know where it acts. And we can calculate the magnitudes of the resultant by basically equating this. If we know what the horizontal force acting here is, we know that has to equal this. If we resolve vertically, we know that this has to be true. We do know what this is, and what this is. So we can calculate the magnitudes of these other numbers, which are these two here. If we know what this is, we can calculate the value of the resultant. And if we know the magnitude of the resultant, we can then take moments about any single point we want to be able to figure out exactly where that point acts. And what's done here is, let's assume that it acts 2/3 of the way down this line. We could kind of imagine that because it's a linear distribution. If we assume that it acts 2/3 down here, and we take moments about this, point, we find that there's no net moment in our system. And so it has to be that it acts at that point. So the last one is kind of a complicated one, but it does make the point that all of these three methods should give you exactly the same result. They're not different at all. They just are different ways of doing the calculation. So the last one's kind of overly complicated, but it does make the point, and if you feel so inclined, you might check it. All right. So let's switch gears. So we made the point that forces acting on structures is really the equivalence of buoyancy, or buoyancy is the equivalent of that behavior. And it results because if you look at the pressure distribution on, say, a structure, and you remove the fluid from inside that structure, then all of a sudden there's an imbalance of the fluid pressures at the bottom, overwhelming what was in equilibrium because of the weight of that container. And that net force is the buoyant force. And so again, if we look at structures, we can calculate free body diagrams of exactly what's going on. So here's an example to calculate what is the tension that gets applied in this cable if you have a buoy which has a certain volume. So again, we know that the buoyant force is going to be acting upwards against gravity. We know the weight of the buoy, whatever it's made of, steel or whatever, is acting downwards. And we can presume that in the cable there's some tension that's acting downwards. So that's basically what's given in this free body. The reason for buoyancy is that the fluid pressures acting downwards are less than the ones acting upwards at depth. We know that. We just did that for our container that looked like this, where there's a bigger force acting up relative to a smaller one. This is what it would look like on a structure, but it's basically the same idea. If we resolve things vertically, we have the weight and the tension acting downwards. We have the buoyant force acting upwards. We know the buoyant force is equal to the volume of fluid displaced multiplied by its volume. Volume of fluid displaced multiplied by its unit weight. And so if we know what the weight of this is, if we know what the buoyant force is, then the only thing that we need to calculate is the tension. So again, just resolving behaviors. And so all that's important, I guess, to remember here is that the buoyant force is the volume, the unit weight of the fluid that's displaced. It's not the density of the structure, it's the density of the fluid that's displaced. And for instance, if it were to be a cork that has some weight to it, you need to include the weight of that cork against the buoyant force which is pulling up. If it's neutrally buoyant, you can always apply a tension. If it's neutrally buoyant, then this tension will be zero. Neutrally buoyant means it's just floating, not going up, not going down. It means that the buoyant force and the weight are exactly in equilibrium with each other. And it doesn't have to be tethered in place. Okay? So you'll get to do some of these, I guess, in your homework, which is live as of now. So the other thing that we can also talk about is stability. The one thing I didn't mention, which I should mention, is that the buoyant force it acts, we need to know where it acts. Center of buoyancy. Center of buoyancy is equal to the centroid of the displaced volume. Fluid volume. So I guess as an example, if we had a square block, then the center of buoyancy would be at the centroid of that block. So in other words, you could draw lines here, and it would be on that axis. If you drew lines on the top, it would be on that axis. And if you drew lines on the side, it'd be on that axis. So the bottom line is that it's dead in the center of this. It's at the centroid of this volume. We've talked about centroids of planes because that was relevant to us. But the centroid of a volume, I don't have a volume on me, but the centroid of a pack of cards would be the dead center of that pack of cards. And so that is where the center of buoyancy acts. And so this is the location where FB acts. If this has a mass, then the center of gravity of that thing, if it was uniformly distributed, would also be the same point. And so if it was submerged, the 2 points would be coincident, but that's not always the case. And so that relates to stability. So stability is the propensity of something to capsize, if you like. The easiest stability problems for us to do are for things that are submerged. So in other words, the whole body is below the surface. If the whole body is below the surface, the center of buoyancy is going to be the centroid of that displaced volume. And so no matter how you turn this body around, it will always be at the same point. If this structure was weighted so that there was more weight in the bottom, such as in the keel of a boat, than there is in the top, then the center of gravity, instead of being at the centroid of this mass, would be below it. That's probably good, right? If the center of gravity is below it and you pull this over a little bit, then now, if you look at the moment that is applied on this structure, the net moment is one that pulls it in this direction, right? This is pulling downwards, this is pulling upwards, so it'll tend to push it in this direction. If it pushes in this direction, it puts it back in its right place and it doesn't go anywhere else. If the center of gravity is above it, the exact opposite happens. You pull it off course by a wave by a small amount, and now the force acting downwards and the force acting upwards give it a moment or a couple that turns it in this direction, and it gets progressively worse, and it will just go until it'll turn upside down completely until it's in the configuration where the center of gravity is below the center of buoyancy. So stability, and you can probably rationalize that in the things that you've done. Exactly the same thing applies for floating bodies, but it's slightly different because in a floating body, all of a sudden, the area that's submerged, in other words, the area that's included in this contour here, changes as you tilt it over. It was this area here, and now it's a slightly different area. The center of gravity won't change because it's based on the cargo that's in this ship. It's fixed, hopefully, in one place so it doesn't move. And so the center of gravity, the balance point that you'd take this ship and you'd hold it around and it wouldn't move, would always be the same. But the center of buoyancy will change because it's related to the displaced volume of fluid. There's more fluid volume displaced now on this side than there was on this side, and so the center of buoyancy will migrate over to the right, and it's here. In this particular case, it's good news, right? Because the center of buoyancy, the force acting upwards is here, the force acting downwards is here, and so the moment that it applies turns it back so it's horizontal again. So the boat's horizontal. That's the boat you want to be on. The boat you don't want to be on is where, as in this bottom case, the center of gravity, which doesn't move, and the center of buoyancy below it, if you tilt this boat slightly, now the center of gravity is to the right-hand side of the buoyancy. The net moment that's applied is clockwise, and this will just keep on getting worse, and it will do exactly what we did before. It'll either lie on its side, or it will go completely upside down. And so those are the things that we'll talk about in terms of the final example here. We won't have time to go through. You might look at last year's video. We certainly went through it last year. It's just an example to illustrate buoyancy in a bit more complicated way.